Hello and welcome to my talk. My name is Adam Nichols, and today I'll be discussing some of the measurement, diagnostic, and analysis tools we use here at ARL Penn State for flow noise characterization. Specifically today we'll be looking at volumetric PIV and its decomposition for investigating noise sources. I'd like to acknowledge my collaborators Jeff Harris and Ted Bagwell of ARL, and Alex, Jim, and Kristen from NNO. The flow of interest for today's talk concerns internal or pipe flows, which can often be difficult to measure optically, but contribute greatly to overall system noise in many cases, and they can contribute to flow noise sources that are not well understood or easy to model. So it's important that we're able to use state-of-the-art measurement diagnostic techniques to characterize these sources. And with that in mind, there are two objectives for today's talk. The first is to demonstrate the use of volumetric or tomographic PIV in an internal flow with highly distorted areas, where these high areas of distortion are due to small radius of curvature of the pipe, in addition to the relative thickness of the pipe. We'll benchmark these measurements with measurement techniques that are more established in literature, mainly stereo PIV and LDV measurements over the same domain. The second objective is to demonstrate the application of a low-order velocity field decomposition technique to the tomographic PIV data, and you will use this to characterize and identify flow physics related to noise and vibration. And this method that we'll use is spectral POD. The measurements we'll present here today were performed in the ARL PSU 6-inch recirculating water loop, shown in a schematic in the top left here, where we have highlighted in green what we call the octobox, which is our measurement station. Highlighted in orange is a bluff body that we use to disturb the flow, and basically that serves as our acoustic source for this case. And then further upstream we have highlighted in yellow a flow straightener. So in this, as I alluded to in this work, a split cylinder was mounted upstream of the optical test section. This optical test section is an acrylic pipe surrounded by a water-filled octagonal acrylic prism. This gives us flat surfaces with which we can observe the flow using 4 Photonics V1212 cameras mounted in a cross pattern around the test section. Synchronously with this PIV measurements, we acquire pressure transducer data on either side of the cylinder, which is shown here in the bottom right. The cylinder is just upstream of the measurement location, and again that provides a flow disturbance that we can say we somewhat understand this flow disturbance. It's somewhat well understood already, and we can benchmark some of our analysis techniques on that. So the reconstructed volume that results from the tomographic PIV is a thin disc across the pipe section, and just for reference, the flow rate in this experiment was 200 gallons per minute. The velocity fields were measured at 1024 Hertz for 12,000 snapshots, and the pressure was recorded via the pressure transducers at 2048 Hertz. The cross configuration of the tomographic PIV setup is shown here around a caricature of the pipe flow with the cylinder to the left upstream of our measurement volume. So we have our cameras set up with 1 and 2 being on the horizontal axis and 3 and 4 being on the vertical axis. And next to the cameras in these black squares, we have movies of the actual particle maps that are being recorded. So these are 2D particle maps that we use to reconstruct a 3D disk volume of velocity field in the case of tomo PIV. Now, as tomo PIV is a relatively new measurement technique, we can also process this data in a stereo orientation. So this gives us 3-dimensional velocity fields only on a thin 2-dimensional plane. So we can process that using the 2 pairs of cameras, C1, C2, and C3 and C4. And that gives us 3 ways of measuring the velocity in the same part of the flow. And we can benchmark those techniques against each other to see how well the tomographic PIV is performing. And since those are correlated in that they use the same image data set, we also performed LDV across the center line of the pipe, which gives us an uncorrelated measurement of the velocity field with which to baseline the other techniques. Now again, it was alluded to earlier that in this flow we have very high distortions in the optical field, and with all tomographic PIV, calibration is key. So a major component of this work was establishing a volume calibration for these cameras so that we could accurately triangulate each particle in three-dimensional space. The results of those velocity measurements are shown on this slide. At the top, I have a contour of the axial mean velocity on the left and the mean vorticity on the right. There's a green bar that overlays where the LDV was performed in these fields. The contour maps are one image plane from the center of the volumetric disk, and we can see that we capture the wake behind our cylinder upstream of our measurement location. In the bottom plots, on the left, bottom left, I have the mean axial velocity normalized by the bulk velocity for the tomographic PIV in black and the two stereo setups in red and blue. And then overlaid on top of that is the LDV profile. And we can see that in the center of the pipe, that's denoted by a R over R of 0, we perform quite well. We appear to match the LDV pretty accurately, but as we go away from that center line, where we have the least amount of distortion, we can see that all three of the PIV estimates start to underpredict the velocity field, and this could be due to two things. One, it's a shear layer somewhat in this flow, and PIV fields tend to underpredict the velocity in a shear flow due to a smearing effect, but it could also be due to the higher distortion that's characteristic at the near wall locations. On the right, we have the RMS of the axial velocity normalized by the bulk velocity again for the three PIV setups in the LDV. And in this case, it's quite evident that we are spatially averaging somewhat, as all three of our PIV setups, while they match each other and have the characteristic profile we're looking for, they underpredict the fluctuations at the center of the pipe. And so this is kind of evidence that while we don't match the LDV, it seems as though the TOMO is performing quite well. Since this is a flow noise talk, we're of course interested in the temporal information captured by our measurements. So shown on the left here, we have the power spectral density of the velocity field, captured the tomographic velocity field at the center line of the pipe. So on the vertical axis of these plots, I have the power spectral density of the horizontal, vertical, and axial velocity components, plotted as a function of radial distance across the pipe at the center line of the pipe and frequency. So we can see, especially in the horizontal and axial components, we're peaking at around 22 Hertz. So this hopefully corresponds to the shedding of the cylinder. So to verify that, we can look at the power spectral density of the pressure transducers installed just upstream of our velocity field measurement location. So in this plot, again, I have power spectral density of pressure plotted versus frequency for pressure transducer 1 and 2, which are arbitrarily named. These open face circles in red and blue denote a baseline case with no cylinder installed. The X's denote a cylinder installed case. And we can see that from these red and blue measurements that we're picking up a lot of the background turbulence of the pipe flow. It's hard to discern the specific effect of the actual shedding across the cylinder. But by subtracting these two, we can see quite clearly in this black line, DP cylinder, that our cylinder shedding stands out pretty strongly. And that happens to occur at about a frequency of 22 Hertz, which matches what we see in our velocity field information. So we can verify, or we verified, that we're capturing relevant temporal information by our TOMO PIV measurements, and we're going to use this DP cylinder signal as an indicator of our hydroacoustic features of interest. Having baselined our volumetric velocity measurements, we can turn our attentions to the second objective of this talk, which was the application of a velocity field decomposition tool, the proper orthogonal decomposition, or POD. So on this slide, I have shown the space-only or snapshot versions of POD in addition to the spectral POD shown on the right. And without getting too deep into the mathematical details, the difference between these techniques is the decomposition results. So in the case of the snapshot POD, you arrive at a basis set of modes that are optimal with respect to turbulent kinetic energy. However, they don't represent a true occurrence of the velocity field. They actually, the modal shapes themselves are representative of many processes happening at once that contribute to the turbulent kinetic energy. So we can't, gives you something of an interpretability problem when you look at a mode and try to tie it to a physical feature of the flow. In the spectral POD, you arrive at a basis set of modes that are time frequency modes. So they evolve at set frequencies, as these are based on the Fourier decomposition in time, and they are still optimal with respect to the turbulent kinetic energy that they reconstruct at a single frequency. So all of these modes are uncorrelated to all of the other modes at all of the other frequencies, and they represent a true building block of the flow. So if you pick a mode at a certain frequency, it evolves by itself and it has nothing to do with the other modes. So you can really interrogate or characterize a velocity field a lot deeper with this technique than the space-only POD. So after applying the spectral POD, we can look at the entire decomposition space and see how each mode contributes to the turbulent kinetic energy of the flow. So on these plots shown here, we have mode number versus frequency. So these are the modes at each frequency bin. And the turbulent kinetic energy is plotted on the contour, where each mode is normalized by the total turbulent kinetic energy within a single frequency bin. And what we can see is that the dynamics are very compact. The energy decomposition is very compact, where we expect it to be at the shedding frequency. So if we look at the 22 Hertz bin, zoomed in on the right, it's pretty evident that most of the energy in that bin is in a few POD modes, and those correspond to the large-scale shedding of the cylinder. And interestingly also, at around 48 Hertz, we have another slight dip, which indicates that in that frequency bin, there's something a little bit more coherent happening. All of the rest of the bins, it's very evident that you need to retain a whole lot of modes to represent what's going on there, and that's indicative of somewhat sparse dynamics. After deciding which modes we're interested in looking at in particular, we can look at the spatial features of these modes. So this is the real component of the complex modes for mode 1 and 2 in the 22 Hertz frequency bin. And we see that the spatial structure, very much indicative of large-scale shedding behind a cylinder and a pipe. If we look at that secondary frequency bin that we had denoted from the previous slide, the 48 Hertz bin, where again on the top we have mode 1, and the bottom we have the mode shapes of mode 2 for the different velocity components. We see that there's an added feature in the flow that wasn't obvious in any of the other measurements that's contributing to our acoustic source. So with that, I'll take some questions.